A little crazy. All right, good morning, lads and ladies. Welcome back to MAC 1140. Today we're going to begin charging forwards into chapter 3, which is an exciting section for us because we're going to start taking all of this stuff we've discussed kind of regarding functions in general, and we're going to be applying them and using what we know to analyze different families of specific functions. So chapter 3 is focused on polynomial and rational functions. And that's what we're going to begin on today. After that, we're going to move on to talking about logarithm and exponential functions to try and kind of get us a good feel for what all these different functions look like. And we're going to apply all of the stuff that we've learned in chapter 2 to each of these families of functions. Before anybody asks, I have not graded your tests yet. I will do my best to have them graded for you by Thursday. My usual rule is a 1-week turnaround. I want to assure some of you, I've gotten a few emails. I don't know if anybody from this section has sent me such an email, but I've gotten some emails saying, oh, I did so badly on this test. And, I've got like a 22 on the test or something like that. Should I just drop the class? The test isn't graded yet. So that score is just the free response, or sorry, just the true, false, and multiple choice. The bulk of the points come from the free response, and I haven't entered any of those points yet. So don't worry, the grade you're seeing in there right now is not your final grade on the test. I haven't graded the tests, have not entered the scores for the free response questions, so those are going to change. So please don't panic. But they will be graded by Thursday. All right. Of course, I did post an announcement. If you haven't taken the test yet, for whatever reason, I need to get you to take that test. And I'm not too picky about why. If you missed the test because you had a flat tire or something going on or whatever, whether we've talked about it or not, please read that announcement if you haven't taken the test and make sure you get the test completed in one of the 2 makeup sessions that are going on this week. So all of the details are there in Canvas. Let's get this thing going. This is MAC1140, section number 008, which means we're talking about pre-calc. And today is the 28th of September. Today. We're going to start talking about polynomials. Specifically, we're going to go through section 3.1 on quadratics. And if there's time, we may move a little bit beyond that. We may talk about section 3.2 on polynomials and their graphs. So 3.1 is kind of a quick pass at all the stuff you should remember about quadratics from your previous algebra classes, just to kind of make sure we fill in any gaps that are missing and to also kind of give us an opportunity to look at these objects that we know pretty well from our past lives and see them in this slightly more sophisticated way, see them from this perspective of what we know now. So without further ado, I'm going to go ahead and jump in on this. You will have a homework opening up today. It's going to be on 3.1 and 3.2. And I'll just include problems that are relevant for the material that we get through today. So let's see where we end up. All right. So quadratic functions. These are things that you guys have no doubt seen before. I would say a quadratic function is any function which can be expressed can be written in the form, let's say f of x equals ax squared plus bx plus c. Right, this is certainly something we've all seen before. There is a little bit of a difference in terminology. So most textbooks, probably your previous algebra class, called this the standard form for a quadratic. Your textbook uses that word standard form for something else. And I'll share that with you here in just a second. But for us, a quadratic is any function that can be written like this, which is really just a degree 2 polynomial, if you know those terms. But you don't need to know those terms. The only catch is here, we don't want a to be 0. If a is 0 in this expression, then this term isn't really here. So this isn't really a quadratic. It's the x squared that makes this a quadratic. Okay. Standard, which most books call the vertex form of a quadratic. So you can take an expression of the sort that I've given you here and rewrite it to rewrite any quadratic x squared plus bx plus c in the form f of x equals a, where this a is the same as this a times parentheses x minus h squared plus k. And this is what your book calls the standard form. However, most people know this as the vertex form because of its connection to the graph and an important feature on that graph. One of the reasons it's so nice to write a quadratic in this form is because you can see this as a transformation of x squared, right? If you compare this guy to just good old-fashioned y equals x squared, x squared is the parent function for this guy. So what are we doing? We're translating, we're shifting horizontally by h units. If h is positive, that means you're shifting to the right. And then you're shifting up by k units if k is positive. If k is negative, you're going down. And there's also this vertical scaling factor here, a. So any quadratic, turns out, can be written in this form, which means you can pretty easily come up with the graph. So the graph of such a function, there's many possibilities, but I'm going to try to draw this kind of as generally as I can. I'll assume h and k are both positive. So this point right here is h comma k. And if a is positive, the graph will look something like this. All right, it's just the graph of x squared. It's been shifted to the right by h units and shifted up by k units. So this point right here is called the vertex. Now I'd say the shape of this graph, we all know the name, right? That's a parabola. All quadratic graphs are parabolic. The parabola opens up if a is positive. All right, so if you have the quadratic in this form, you can draw the graph very easily. You just have to ask yourself, okay, where's my vertex? Well, I've shifted x squared to the right by h units and up by k units, so that vertex went over here and then up here. And then if a is positive, that, you know, stays like this, maybe stretched out a little bit, maybe compressed a little bit, but still the same basic shape, still opening up. On the other hand, if k is negative, or sorry, if a is negative, put the vertex in the same spot here, h comma k, assuming both of those are positive. Your parabola is going to look something like this. We call this opening down. Right, so the graph on the left, we call this the parabola opening up because the kind of bowl shape is pointing to the up, the open end. And this guy, we call this opening down because the kind of open end of the bowl is pointing down. One of the big questions is, how do I take a quadratic from this form and put it into this form? And we're going to address that. There's a few ways to do it. If you have the graph, you can read off the vertex. Here, still h, comma k. But there are also kind of pure algebra procedures that allow you to take a quadratic from this form into the vertex, or text we call standard form. The thing you need to know how to do is, in order to move from this form to this form, is called completing the square. I'm going to show you how to do that now. After that, I'm going to prove the quadratic formula for you, which is not a hard thing to do. It involves completing the square. And that's pretty much going to be the end of our discussion on quadratics, right? Because you can graph any of them as a translation or transformation of x squared. And you can do all the things that you want to do just by either completing the square or using the quadratic formula. So once we prove that quadratic formula by completing the square, you'll have all the good stuff. Maybe one last comment before I move away from this picture. If your parabola opens up, then there's only one local min, right here. It happens to also be an absolute or global min. We haven't discussed that terminology, but there is a min here. If your parabola opens up, then the vertex is a min. And if the parabola opens down, then that vertex is a max. So to find the max or min for any parabola, you just have to find the vertex. So again, it's sufficient to get it into this form, because then you can read off the vertex from this form. Let's take a specific quadratic and do all that stuff. So completing the square is an algebra process that will allow you to take something like this and rewrite it like this. The procedure is not terribly complicated, but it takes a little getting used to. So let me show you how to do it. We can do it through examples. So, for example, let's express f of x equals 2x squared minus 12x plus 13 in standard, aka vertex form, which is this guy. To do that, we're going to complete the square. Completing the square means taking this quadratic and rewriting it as a kind of perfect square piece plus some other constant, maybe with something multiplying it out front. So your first step is to take this 2x squared minus 12x plus 13. From the first two terms here, from the x squared quadratic term and the x, the linear term, I'm going to factor out the 2. I'm going to let the 13 chill out here. I'll write this as 2 times parentheses x squared minus 6x, and then close parentheses plus 13. the next step after that is to take this number right here, the -6, divide it by 2, then square that. So when I teach this in other places, I call this the magic number. So you got to find the magic number. Which here, so after you've done this first step of factoring out whatever the lead coefficient is from these first two terms, the number that's going to be here is this b over a. So that's the general way to do this. You're going to take b over 2 and square it at this step, which is really b over 2a. But I read it like this because you've already factored out the a. So what is b here, your linear term, after you factor this out? That's -6 over 2 all squared.
I have a question real quick.
Sure.
Is it always 2 or is it just for this problem? Since it was the one that was factored out.
No, it's whatever the coefficient of x squared is.
Okay, so b over the coefficient of x.
Yep, and that's why, so some people, if you look for a really general way of writing this, you'll see they write it as b over 2a, because if you're working from this version, right, your textbook does it like this, where they factor this thing out first. You don't have to do that, but it makes life a little bit easier. So if you're thinking of a, b, and c as being these numbers, your first step is to factor out whatever a is, right? Whatever this is, to get this. And then you take this b here and you divide it by 2a. So here I would be taking -12 and dividing it by 4, and that would give me the same thing as -3. Square that, you get 9. So once you find that magic number, you're going to add it and subtract it right after the x inside the parentheses. So I'm going to write here +9 -9. I know that feels a little weird, but just roll with me. See that the stuff in the parentheses hasn't changed, right? This +9 and -9, this is 0. So this whole line really is equal to this whole line. But by giving myself a +9 here, I can factor these three things as a perfect square. So then within this, I'm going to factor just these three, right? I treat that as its own quadratic. And to factor this, we use the AC method, which I'm assuming you remember from your previous algebra classes. So you multiply this 1 and this 9, and you say, okay, I need two numbers that multiply to 9 and add up to -6. Well, that's x minus 3 times x minus 3. Those two numbers are -3 and -3. Because -3 times -3 is 9, and -3 plus -3 is -6. Then I still have this -9 close paren plus 13. So that's 2 times x minus 3 times x minus 3 is x minus 3 squared. And we still have our, I'm going to stop using the blue now, -9 and plus 13. And then you distribute the two and combine your like terms. So this is 2 times parentheses x minus 3 squared minus 2 times 9 is 18 plus 13. And -18 plus 13 is -5. So this guy in that vertex form is this.
I got a question. How did you get -18 again?
I distributed this 2. So this 2, right?
Okay.
Here and he goes here. So the 2
Okay.
times -9 is the -18.
Gotcha.
There was a question in chat. What do we find if we use the quadratic formula? I'm going to talk about that in a minute. That's finding the x-intercepts. That's what that does, or we call these roots.
Also, excuse me, but what did you write before the sharp? Right, right before.
Magic number.
Oh,
Yeah,
find
I'm
magic
sorry,
number.
I'm old enough that this still means number sign to me. But yeah, find the magic number.
Thank you.
All right. Any other questions? Let's take a second and really see how comfortable we feel with this process, because this is something you're going to have to do on the test.
Is finding the magic number is just finding the vertex? You use negative b over 2a?
Sort of, but we're squaring this. So you take the, and there's no negative here. It's just b over 2a all squared.
Is that a different formula to find that number?
It's coming from the same sort of place. The vertex formula that you've remembered from a previous algebra class is a consequence of this, because the quadratic formula is a consequence of this.
So do we always use b over 2a squared?
Yep, for your magic number, it's going to be b over 2a squared, and that's where a is this, b is this, and c is this in the original form.
Why didn't you times a by 2? Why wouldn't it be negative 6 over 4?
Well, so if I take a, b, and c here, I was working with the numbers I had in here. I don't mean to confuse you. I factored out the 2 first. So if you want to, you could write this. This is negative 12 over 2 times negative 2, if that makes you more comfy. Yeah, in fact,
Okay.
let me go ahead and write it like that. That way, this is all consistent. But it's the same thing, right? Negative 12 over 4 or negative 6 over 2. We're still going to get negative 3, which we need to square, which is 9.
Okay, thank you.
Yeah, of course. Other questions? Yeah, so Mel says, where's the +9 and -9 coming from? I'm choosing to insert those, which is a little bit sneaky. So this is why we call this a magic number. We cook it up on our own, and then we add it and subtract it, because doing that will always make the first 3 terms factor as a perfect square, which is why this is called completing the square. So you see this 9, this +9 right here is exactly what I needed to add to x squared minus 6x in order to make it factor as a perfect square, this x minus 3 all squared. If I'd added any other number here, this wouldn't have factored this way. So the 9 is special. Each quadratic has its own special or magic number, such that when you add it to the first 2 terms, the result is going to give you a perfect square. And then if I'm going to add this 9, I have to subtract it. I can't just add the 9 and say, oh, that didn't change anything. Of course, that would change things. So if I add something inside here, I have to also subtract it to kind of balance things out. And the 9 is special. It is the special number or magic number associated with this quadratic that will allow me to factor those first 3 terms as this perfect square. So the perfect square right here is why we call it completing the square. Some other things I might want to do here, I might want to state the vertex. So from this form, I can tell you what my vertex is. Right, and we don't need that formula from college algebra or wherever, the negative b over 2a thing. You can just read it off right from this form. So h is 3, not negative 3, mind you, because there's a minus built into this form. And k is negative 5, right? Because this form is this plus k. So here, this is plus negative 5. So my vertex would be the point 3 comma negative 5. I can sketch a nice graph of this function, or at least a reasonable graph of this function. Maybe not perfect, but using my transformation rules. And say, okay, I'm going to come out 3 here. I'm going to come down negative 5 here. There's my vertex. And then I'm just going to draw a parabola. It's going to open up because a, the lead coefficient, is 2. So my parabola looks something like this. We could ask for the domain. for the range. The domain, we could argue either from the graph or algebraically, since this function has no domain red flags, right? There's no variables downstairs in fractions. There's no variables under even roots or anything like that. Because this guy has no red flags, we know the domain is going to be all real numbers. Or looking at the graph, you know what the graphs of parabolas look like. They keep going forever and ever in this direction and off to the left. So yeah, this arrow continues up like this, and so it'll eventually reach over here anywhere you like. This arrow continues up like this. So either from the graph or thinking about the algebra, we see the domain is all real numbers. What about the range?
Would it be
negative
bracket?
5 or 2? Oh, sorry.
I
You
hope
go.
there's more than one people who want to answer. Yeah,
-5 to infinity.
very good. Yeah, and I heard you the first time. It's a bracket on the -5, right? So we do actually hit -5. All right, so once we complete the square and put the parabola or quadratic into this nice vertex or standard form, it's easy to see the range. And that's maybe not so easy to see otherwise. This is another reason why it's really nice to put these things into this form. You get the graph, from the graph, you get all this good stuff. Any questions on any of these procedures? Or how we found any of these stats? Soon we will want to come in here and find these x-intercepts. That's a big deal. Not just for quadratics, but for any polynomial. There was a request though to do one more example like this, so we can do one more example like this. Which one is that? Switch graph, find domain range. Sure, let's do this one. So same sort of deal. Let's express f of x equals 5x squared minus 30x plus 49 in that vertex or standard form your book calls it. And we'll sketch the graph. And we'll find min or max values. All right. Before I even get started here, when I go looking for those extrema, the min or max, is it going to be a min or a max and why?
Gonna be a min because A is positive.
Yeah, very good. This number a is positive, which means my parabola is going to open up. So that vertex is going to be a min value, right? The lowest point on the graph. All right, let's do it. If I take 5x squared minus 30x plus 49, first may be worthwhile to say, okay, a is 5, b is -30, c is 49. Always nice to know that. Then from these first two terms, I'm going to factor out the 5. So I'll have 5 times x squared minus 6x, close parentheses, plus 49. And now I need to complete the square in here. So my magic number should be over 2a all squared. B is -30, a is 5. So this is -30 over 2 times 5 is 10. All squared. Oh, it looks like it's going to be 9 again, right? So -30 divided by 10 is -3. And that squared is +9. So again, my magic number is 9. Oh yeah, this is actually very similar to the previous one. So this is 5 times x squared minus 6x, and then I write plus 9 minus 9. Right after that x, plus 49 on the outside still showing. And in the same way we saw the last guy, you take just these first three terms and factor them. That's x minus 3 quantity squared. So this is 5 times parentheses, parentheses, x minus 3 close parentheses squared. The minus 9 is still here, and then plus 49 is still here. So again, I'm just factoring this first three. This is kind of going against what we normally learn about polynomials and factoring, is that you don't want to factor like a part of the polynomial, you need to factor the whole polynomial. But this completing the square business is a little different than saying I'm going to factor the whole polynomial, so different rules apply. Now I'll distribute this 5. One copy of the 5 is going to go to this piece. Another copy of the 5 is going to go to this piece. This will be 5 times parentheses x minus 3 squared. And then 5 times negative 9 is negative 45. And I have my plus 49. And negative 45 is positive 49. Is positive 4. So we arrive here. So my vertex that's positive 3, comma, positive 4. Remember, there's a minus sign kind of baked into this. Or if you want, you can think of it as a transformation, right? That's really the way to do this. Is if you look at just this piece on its own, that's x squared shifted to the right by 3 units. So the vertex should have x coordinate 3. And then shifted up 4 units. Oh, okay, so the vertex should have y coordinate 4. That's it. The 5 is going to stretch things vertically. But your pictures don't have to be perfect here. It's 3. It's 4. Parabola opens up.
Excuse me.
Yes.
Where did you get the 4 from?
Negative 45 and positive 49. So we combine these two like terms.
Oh, I'm sorry. I thought you wrote 44. I don't know.
Oh, no, yeah, sorry. This is a 49. Alrighty, so there's my graph. We can do the same thing, domain range. In this case, though, we wanted to find the min or the max. So the min value here, let's say the min is at x equals 3. And the min value smallest output is 4. So hopefully this isn't too intimidating. You guys have seen plenty of parabolas in your past. The only new thing here is completing the square, right? Which is an important procedure. We will use it later in the semester when we talk about conic sections in general. And you'll use it quite a bit in Calc 2 when you get to certain integration techniques and elsewhere. Any questions on what we did here?
Will the minimum value or maximum value always be the y? If x equals 3 and the minimum value is 4, does that mean it'll always be the y value for the minimum maximum value?
It's true that for a quadratic, because the graph is always a parabola, the min or max value will always be the y value of the vertex. Yeah.
Okay.
So finding x intercepts. Quadratic formula. So sort of the simplest way to find x-intercepts is to factor the original polynomial, right? If you're lucky enough that your original polynomial factors, then you can find the x-intercepts by factoring. But in many cases, these quadratics do not factor. So what we need is some way to find the x-intercepts in those cases. So if the quadratic factors, the quadratic can be factored. What most people learn is called the AC method. Do that. For example, I want to find the x-intercepts for, how about f of x equals x squared minus x minus 2. This guy can be factored. And it's not too hard. You take this number and this number, right, which are c and a. You multiply them. So a is 1, c is -2. 1 times -2 is -2. And then you find two numbers that add up to the middle guy and multiply to a times c. So a times c here, purple. C here is 1 times -2. B here is -1. So we need to find two numbers which multiply to a times c, which in this case is -2, add up to b, which is -1. So what two numbers multiply to -2 and add up to -1? Those two numbers are -2 and +1, right? -2 plus +1 is -1, and -2 times +1 is -2, which means that you can rewrite your function as x minus 2 times x plus 1. That's it. This is factored. So the x-intercepts setting x equal to 0 and solving. Since we've already factored the thing, setting it equal to 0 is not hard. So here, 0 is equal to, I'll write it out, x squared minus x minus 2, which we've just factored as x minus 2 times x plus 1. So now I can set each of those factors equal to 0 on their own. And we get the two x-intercepts. Factoring can be a little bit harder if the lead coefficient isn't 1, but the AC method still works. You still multiply a and c, and then find two numbers that multiply to a times c and add up to b. And then you would factor by grouping after rewriting the middle term. If the quadratic cannot be factored, so you need to practice those factoring skills, right? If you're rough on factoring quadratics, you need to practice that. It's a skill that you must have. It needs to be not just okay, but like really good. However, if the quadratic does not factor, by hand, then we use this theorem called the quadratic formula. What this theorem says that ax squared plus bx plus c will be equal to 0 if and only if x is one of the two following numbers: negative b plus the square root of b squared minus 4ac over 2a, or negative b minus that square root. So we usually write that as a plus or minus here. There is a way to remember this, which is a little bit embarrassing, but I am now going to humble myself before you by showing you a way to remember this forever and ever. So find somebody you respect deeply. Find somebody whose admiration you yearn for, you know, your crush or someone in your family that you are always trying to impress, whatever. And then, to the tune of Pop Goes the Weasel, sing this formula. You will be so embarrassed by this procedure that it will stick with you forever. In the same way that you wake up in the middle of the night just as you're about to fall asleep, remembering that super embarrassing thing you did in 6th grade, this will be burned forever into your brain. But you got to do it. You got to go find somebody that you want their admiration and do this. X equals negative b plus or minus the square root of b squared minus 4ac all over 2a. You see, you do that, and it's so shameful that it sticks in your brain forever. I promise it's effective. You guys have seen this, no doubt, in high school, maybe middle school, probably also in college algebra, but maybe you've never seen where it comes from. Before I prove this, I am going to prove this for you, right? So down here is going to go the proof. Before I prove this for you, I want to rewrite it like this. It's negative b over 2a plus and minus the square root of b squared minus 4ac over 2a. Just splitting up the fraction like that. Because by thinking about it in this way, I will be able to show you some cool geometry. For example, here's h, right? That formula that, who was it? Was it Chris that was asking about that at the start of class? So this is telling you, go to your vertex here, your x value of the vertex, and then walk either to the left or to the right some amount. All right, I'll talk about the geometric interpretation a little later. Let's prove the thing. So what I'm trying to do is solve the equation 0 equals ax squared plus bx plus c. And I want to do this in full generality. I can begin by factoring out the a from the first two terms. That'll give me x squared plus b over a x plus c. We're going to complete the square. Now I'm going to take that magic number, b over 2a all squared, and I'm going to add that and subtract it inside here. So that's x squared plus b over a times x plus b over 2a squared minus b over 2a squared. Close the big paren, plus c still over here. And then these first three terms, it's a little bit harder to see without numbers plugged in, but these first three terms will factor nicely. Two numbers that multiply to b over 2a all squared and add up to b over a, that's x plus b over, let's see, what's this going to be? B over 2a all squared. And then you have your minus b over 2a squared here, and your plus c. You can check. If you were to FOIL this out, your first would be x times x, which is x squared. Your outers would be b over 2a times x and x times b over 2a. If you add those up, you get b over a times x. And then your lasts, b over 2a times b over 2a is b over 2a all squared. So these first three terms really do factor like this. Just to be clear here, these three pieces are what I have factored here, just those three. Everybody with me so far? Okay, so this is all supposed to be equal to 0, right? So I can subtract the c over. C is equal to a times this big parentheses thing, x plus b over 2a all squared. And then this last term, let me clean this up a little bit. This is minus b squared over 4a squared, like that. Still have these big parens here. All right. From here, we've got some choices. Let's see, I could divide both sides by a, or I could distribute the a through, and then we'd have to divide by it later. Let me distribute the a through. So this is going to be a times x plus b over 2a squared minus this term times a. So if I multiply b squared over 4a squared by a, I'm going to get b squared over 4a. All right, one of the a's will cancel. So in this line, I've just distributed the a here. Take this a, I distribute it to this term and also to this term. And that takes this square downstairs and changes that a squared into just an a. Now I can add this piece to both sides. So I'll have b squared over 4a minus c equals a times x plus b over 2a all squared. I'll combine like terms over here. So to do that, I need to have a common denominator, right? This is c over 1. This is b squared over 4a. So I multiply this by 4a over 4a, and I get b squared minus 4ac all over 4a.
I have a question.
Mhm. What's up?
So why does 4a squared end up being 4a again?
I'm distributing this a. So from here, I'm going to distribute that a to this term and this term. And if you take, I'll do it off to the side here, a times b squared over 4a squared, that's ab squared over 4a squared, and you can cancel one of the a's. So that's b squared over 4a.
Okay, thank you.
Cool. Yeah, not too bad, not too bad. We're almost done. My next step is going to be to divide both sides by a, and then I'll take square roots. So when I divide both sides by a, that's multiplying both sides by 1 over a. I get b squared minus 4ac, this familiar looking piece, right? Over 4a, and I want to divide both sides by a, so I'm going to multiply by 1 over a. And over here I have x plus b over 2a all squared. When I multiply these fractions, the top times 1, well, 1 times anything is that thing, it stays the same. The bottom, 4a times a, is 4a squared. So this is what I have. We're almost done. My last few steps here, I take square roots on both sides. When we do that, we get a plus and minus. So I'll have a plus and minus square root b squared minus 4ac over 4a squared is equal to, now on this side, I just have x plus b over 2a. I'm going to subtract this term over here and also give the square root to the top and bottom separately. So this will be negative b over 2a, this term subtracted over, plus and minus square root b squared minus 4ac all over the square root of 4a squared. This is now equal to x. And hopefully you see that this is your quadratic formula. This is it. i.e., I'll write the x on the left-hand side. X is equal to negative b over 2a plus and minus the square root of b squared minus 4ac all over the square root of 4a squared. Well, the square root of 4a squared is 2a, which is the quadratic formula. Right, you can write it either way. Right, it's one fraction because they both have the same denominator, negative b plus and minus the square root of b squared minus 4ac all over 2a. But I prefer to think of it like this. So that's the proof, right? And if you've never seen that before, congratulations. Finally, after all these years of math teachers just preaching the quadratic formula to you, you know where it comes from. I can't tell you how relieved I was to see this the first time. Like, where the fuck does this formula come from? And why am I being forced to memorize it? And blah, blah, blah. It's really just completing the square. That's all. All we did here is complete the square. It's just instead of numbers, I left the symbols as A, B, and C. And when you do that, you get an equation we could solve, which is pretty dope. You're not responsible for the proof. I'm not going to test you on this proof, but you will need to be able to complete the square on specific quadratics. So if I give you something like the 5x squared minus 30x plus 49 and say complete the square, you need to be able to do that. I do want to talk about a little bit the geometry of this formula just because it's so beautiful. And to do that, I'm going to draw a nice general graph here. Something like this. Okay. So this is our vertex, h comma k. So I know that this x value right here is h, which many people remember is negative b over 2a. Well, why is that the case? If you look at this nicer way of writing the quadratic formula, what this says is to get to the x-intercepts, to get to the x values of the x-intercepts, these things, start at negative b over 2a, and then walk to the right this amount. So this distance right here because of the symmetry is the same. Right? Parabolas are all symmetric about their vertex. They all have this axis of symmetry right down this middle line, right? And d here is that square root of b squared minus 4ac all over 2a. So the geometric interpretation of the quadratic formula is that the first piece, negative b over 2a, tells you your axis of symmetry. And then the second piece, the square root over 2a, tells you how far to walk to the right, how far to walk to the left from that axis of symmetry to get to your x-intercepts. If I call this x1, this point here would be x1 comma 0. And if I call this guy x2, that point would be x2 comma 0, then x1 is really h minus d, and x2 is h plus d. Which are the things you think they are, right? It's negative b over 2a minus the square root of b squared minus 4ac 2a plus the square root of b squared minus 4ac. It's the symmetry in the graph that allowed people to come up with the quadratic formula. It's thinking about it this way that led people there. They said, okay, can I always find this axis of symmetry? And eventually someone discovered, yeah, it's negative b over 2a. Okay, well, from there, I just need to find this distance because it's the same distance left and right, either way. And then they discovered through completing the square that that distance is this guy. Now there's a name for the piece under the square root. It's called the discriminant. If b squared minus 4ac is positive, that means this distance makes sense. I can take the square root of a positive number. So this means you'll have two real x-intercepts. If b squared minus 4ac is exactly equal to 0, that means this distance, because the discriminant comes from the square root of that thing, this distance is 0, which means that the vertex is the x-intercept. There's one real x-intercept. And if b squared minus 4ac is less than 0, then there are no real numbers that make this thing 0. There are no x-intercepts. There are no real roots. This bit about the discriminant isn't in our textbook, but it is a hugely important thing that everybody learns when they learn about quadratics. I just want to remind you. All right, that really is everything we want to talk about regarding quadratics. I think the only thing that may be worth practicing with here is a little bit of factoring. So let me see if I can run you through one more of these AC method type things. So before we say goodbye to quadratics, before we finish up this part of the book, I just want to do one more factoring example where we have to work a little harder. Let's roll it into two things. Let's find the x-intercepts, which, by the way, I'm going to start calling roots. You'll hear me use this word a lot. I use it without even thinking about it. Roots mean the same thing as x-intercepts. Another word that people use for this is zeros. Yeah, someone wants to see that last page real quick. So these numbers, x1 and x2, the x value of the x-intercept, I'll call those roots or zeros. I won't always call them x-intercepts. Just know that those words all mean the same thing. And I know this is a little late, but Megan, I appreciate the kindness regarding my awful singing.
I enjoyed it.
That's very nice. All right, I'm gonna hold here for just a few more seconds. I know someone's still writing the discriminant thing. We're gonna turn back over. Okay, and yeah, so let's find the roots or x-intercepts for a couple of these guys. How about let's see. Let's do f of x equals 3x squared plus 5x minus 2. And the other one I'll call g of x. Let's use for that one some nasty roots, nasty but real roots. 2x squared. Let's do this. Yeah, we used this guy earlier. Minus 12x plus 13. All right. Okay. So for both of these, if we want to find the x-intercepts, we're trying to solve the equation f of x equals 0. And for the other guy, we're trying to solve the equation g of x equals 0. And first, we should try to factor. So if I take f of x that's 3x squared plus 5x minus 2. Here, a times c is 3 times negative 2. It's 6. And b is positive 5. So I need two numbers. Multiply to negative, sorry, to negative 6, negative 6, and add to positive 5. Okay, so can we find two numbers such that when I multiply them, I get negative 6, and when I add them, I get 5?
-1 and +5.
Yeah, very good. -1 and positive 5. Sorry, not -1 and positive 5. -1 and positive 6, right? I have to multiply to negative 6 and add up to positive 5. So yeah, -1 and positive 6. If I multiply those, I get negative 6. And if I add those, I get positive 5. What we do with those two numbers, we come back over here and we use them to rewrite the middle term. So I write this as 3x squared plus 6x minus 1x minus 2. I can do that because they add up to the middle guy, right? I rewrite 5x as plus 6x minus 1x. That's what I do with these two numbers. And then you factor by grouping. So from this first group and from this second group, I will pull out as much as I can. In the first group, I can pull out a 3x, and what's left over is x plus 2. And from the second group, I can just pull out a -1, and what's left over is, again, x plus 2. And as long as you chose these two numbers correctly, this piece and this piece will always match. So then you can factor it out on the right, leaving 3x minus 1, 3x minus 1, and x plus 2. Right, this is the full story with the AC method. If a is not 1, then you've got a little bit more work to do. You have to rewrite the middle term, factor by grouping. Hopefully this is familiar to you, but if you haven't seen this in a while, you needed a rehash of it, here it is. Use this as your prototype if you get stuck. Okay, so f of x factored nicely. Factored as 3x minus 1 times x plus 2. So f of x equals 0 means 3x minus 1 times x plus 2 equals 0. And this is why we care about factoring so much. Once you have the thing in factored form, you're saying this quantity times this quantity is equal to 0. The only way you can have two things multiplying, two real numbers multiply each other and get 0 out, is if one of them is 0. So this means that either 3x minus 1 equals 0 or x plus 2 equals 0. If 3x minus 1 is 0, then 3x is 1, so x is 1/3. And the other guy is coming from this, x is -2. So f of x will be equal to 0 if x is positive 1/3 or -2. And those are your x-intercepts. We're done. If you try to factor g of x, if I take my g of x here, which is 2x squared minus 12x plus 13, then a times c there is 2 times 13, which is 26, and b is -12. You can take 26 and look at all the possible ways of writing this as a product of two numbers, certainly positive here. So 2 and 13 is possible. And since both 2 and 13 are primes, this is it. And 2 plus 13 is not -12. So can I find two numbers that multiply to this and add up to this? No. So we cannot find those two numbers that we need in order to factor this thing. So instead, we need to use the quadratic formula. We can't factor. So use the quadratic formula, which we conveniently just proved. So here, g of x will be equal to 0 if and only if, ready, x equals -b, so that's -12, it's +12, plus or minus the square root of b squared minus 4ac all over 2a. So there's your quadratic formula. And we'll clean this up as much as we can. So that's 12 plus or minus the square root of 12 squared is 144 minus 4 times 2 times 13. Well, 2 times 13 is 26. 26 times 4, what is that? 25 times 4 would be 100. So 26 times 4 is 104. And all of that is over 2a, 2 times 2, which is 4. So this is 12 plus or minus the square root of 144 minus 104 is 10 all over 4. And there's not a whole lot we can do with this. We get the two solutions out. X1 equals 12 plus the square root of 10 over 4. And X2 would be 12 minus the square root of 10 over 4. The square root of 10 cannot be simplified because 10 doesn't have any perfect square factors. So there really isn't anything you can do with the root 10 in either of these. The 12, if you wanted to split these up, you could write this as 12 over 4 plus root 10 over 4. 12 over 4 is 3. So I could write this as 3 plus root 10 over 4 and 3 minus root 10 over 4 if I want to. That's as nice as I can really get these here.
How did you get 10 again?
144 minus, oh no, oh no. Thank you. That's not 10. 144 minus 104 is 40, isn't it? I'm so sorry. You're so polite. Yeah, that was incorrect. I'm sorry. Sorry. Thank you. Okay, so let's come back here. I'm so sorry. 12 plus or minus, this is the square root of 40. 144 minus 104 is 40. Oh, and that's nice. That means this is going to clean up even better. We can talk about simplifying square roots. Yes, I'm so sorry. I made a mistake, right? This is not 10. So we're going to come back here. Okay, this can be simplified, right? The square root of 40.
Is the 4 still in the denominator?
Oh, yeah, a 2. I don't know what my brain is doing there. I'm so sorry. Yes, that's a 4. So 40 is 4 times 10. And that can be simplified. So this is a 4 downstairs here still, yes. And then the square root of 4 times 10, that's the square root of 4 times the square root of 10. So this is 2 times the square root of 10. And then downstairs is still the 4. All right. So, sorry about that. G of x is equal to 0 if and only if x is equal to 12 plus 2 root 10 over 4, or 12 minus 2 root 10 over 4. And these can both be cleaned up a little bit. The top and bottom both have a factor of 2. So I could write this as 12 over 4 plus 2 root 10 over 4. And then 12 over 4 is still 3. And then 2 over 4, you can cancel the 2 and the 4. This becomes a 2. So this is going to be root 10 over 2. And the other one, same sort of thing happens. You have 12 over 4 minus 2 root 10 over 4. 12 over 4 is 3. And then minus 2 root 10 over 4 is root 10 over 2. These would be our x-intercepts. Thank you. Sorry about that mistake. Okay, where are we at for time? We are just about at time here. So let me see if there's anything else we would want to talk about in this section. I don't think so, but let me warm you up for the next section. So the next section is on polynomials in general. Quadratics are special polynomials. I'm going to give you the definition. A polynomial of degree n is an expression of the form. Usually we use p for polynomial, p of x instead of f of x. And it's going to start with an x to the n, right? So the degree is the largest power of x that shows up anywhere. This is allowed to have a number multiplying it, like 2 or 5 or -7. That number, we're just going to call that an. And then you're allowed to have any terms of lower order. So the next term would be like an x to the n minus 1. He's allowed to have a number attached to him. We just call that a sub n minus 1. And you keep going down like this. The second to last term would be a1 times x to the 1. And then the very last term we call a0. So some terminology here. An, the number up front, is called the lead coefficient. A0 is called the constant term. And all the numbers like an minus 1 down to a0, these things in general are called coefficients. Some things here. N is a non-negative integer. And that means that every power of x is a non-negative integer. If the largest one is a non-negative integer, and I'm only allowed to subtract, integers from them, then all of those are non-negative integers as well. And an, we say, is not 0, because I want this to be a polynomial of degree n. And if this number is 0, then this term isn't really here. So this is what a polynomial is. For example, if I have p of x equals 3x to the 5 plus 6x to the 4 minus 2x cubed plus x squared plus 7x minus 6, I would say that the degree here is 5. I could say that the lead coefficient here is 3. And the constant term is -6. So recognizing when something is or is not a polynomial, and in the case where something is a polynomial, being able to tell the degree, the lead coefficient, and the constant term are all useful things. The next step in understanding polynomials is understanding how the factors of the polynomial, and I have no idea how this guy factors, but understanding how the factors of the polynomial affect the shape of the graph. It's true that every factor tells us a root or an x-intercept, but more is true. And that's what we're going to talk about next time, is how the factors of a polynomial affect the shape of the graph. We're also going to talk about something called end behavior, which is kind of what do the arrows do? When you draw the graph, do both arrows point up? Does one arrow point up and the other point down? All of that turns out to be a function of the degree and the sign of the lead coefficient. For the next few classes, we are going to be talking about polynomials in great depth. After this section, there's like 3 more sections that are just about polynomials. We're going to learn how to factor them. We're going to learn how to divide 2 polynomials. We're going to learn how to graph them in great detail, all of that stuff. And you'll see along the way, this is actually a really amazing thing. So I'm going to let you guys go. But before I let you go, I want to tell you about this man, Évariste Galois. And that's my shitty American pronunciation of the Frenchman's name. He would probably not appreciate it. Évariste died when he was 19 years old. 19, right? So your age, maybe younger. Before he died, he contributed possibly the most important breakthrough in modern mathematics. I say modern, this is around the time of the French Revolution. Galois was a revolutionary. He believed in the French Revolution, as bloody as it was. Many other Frenchmen at the time, especially wealthy Frenchmen, which most mathematicians were, because to do math for a living, you had to not work to feed yourself, and back in those days, that meant you had money. Most other wealthy Frenchmen were not pro-revolution, right? So Évariste was kind of at odds with his contemporaries. They didn't like him too much. He ended up getting into a duel. Somebody challenged him to a duel. I don't remember the name of the guy, and I think it had something to do with a girl, but it also had to do with Évariste's opinions on the French Revolution. When he was 19, right, as 19-year-olds sometimes are, he didn't think about it too carefully, and he got himself into a shitty situation. The night before the duel, knowing that he was possibly going to die, every Galois wrote down all the mathematics he knew. And most of it was stuff nobody else had ever even thought of. The main contribution is now a field of mathematics called Galois theory. And Galois theory, among other things, allows us to prove not just the quadratic formula, but also the cubic formula, the formula for roots of a degree 3 polynomial, the quartic formula for the roots of a degree 4 polynomial, and perhaps most important, proves that there could never be a quintic formula. There is not and could never be a formula for the roots of a degree 5 or higher polynomial in terms of its coefficients, just doing like the normal square roots and stuff. So Galois is quite famous. His arguments involved symmetry, movement, all sorts of things that people don't usually think about when they think about polynomials. He was a brilliant, brilliant man, died far too young. And if you ever want to read an interesting man's life story, read about Galois, because it really is fascinating. So just in that one night before he passed away in this duel, he scribbled down some very important thoughts about symmetries and polynomials that turned out to be hugely important. So you can see the separate article on Galois theory here. It's all quite beautiful. The mathematics is maybe a little bit over our heads right now, but if you want to learn this, you can learn this. It's not impossible, and I invite you to do it. I'd be happy to talk to you about it. All right, this is where I'm going to leave off. I could ramble about polynomials all day. Next time, we're going to talk about how to factor big polynomials, how factors affect the shape of the graph, end behavior, and we're going to charge on from there. Dividing polynomials, rational roots theorem, complex numbers, complex roots, all that good stuff. So class is going to pick up here in a big way. You need to make sure that those kind of fundamental algebra skills from your past classes are in good shape, including all the stuff to do with quadratics, which we went over today, and factoring techniques in general. So that's where we're going. And I'm going to leave you guys here. Next time, I will get you your tests back and we will talk more about polynomials. Have a good morning, gang.